In this video, we're going to continue our discussion of rate laws and in determining the order of a reaction. We looked at determining the order of each of the reactants in the last video by inspection. We're going to look at it this time in terms of calculating these values. Now, the problem with the video is that you're not going to be able to see the table at the same time that I'm doing this calculation. So you're going to want to look at the table at the same time I'm filling these values in for the calculation, or it's not going to make any sense. So what we're going to do is to set up a ratio. We're going to set up a ratio between the two reactions. We're going to do the same thing that we did last time. We're going to choose a situation in which, in this case, A was held constant. Now, calculating it takes a little longer, but here's the problem. Unless both A and B were held constant at some point, you cannot do this by inspection. As long as one of the reactants is held constant, though, we can calculate rate order for each of the reactants, even if if in this case B had not been held constant. For reactions 2 and 3, we still could have calculated what our rate orders were. So this is going to be something that we're going to want to use if we see that there are no values in B, in this case B, that are held constant. So I want to show you the process that this is used for. So we're going to, in this case, use reactions 1 and 2 again, and you always want to put the big one on top, the bigger values on top, because that's going to make the calculation easier. So our bigger values were in our second reaction. So we're going to do rate equals K, concentration of A to the M, B to the N. And we're going to put that over the rate for the other reaction. And in order to hold or to make these different from each other, we're simply going to put ones for our first reaction and twos for our second reaction or second experiment. So reaction 2 or experiment 2 is going to be on top, experiment 1 on bottom. And we're simply going to fill in the values. The rate for experiment 2 was 6.0 times 10 to the negative third molarities per second. That really doesn't look like an S, so I'm going to change it. And the rate for reaction 1 was 2.0 times 10 to the negative third molarities per second. And the reason what I'm going to be able to do now, the K values are going to be able to cancel, if that makes sense, because these are constants, and as long as we're at the same temperature, and these reactions have to be done at the same temperature, as long as they're at the same temperature, they're going to be able to cancel. And we had to use a situation where A stayed the same. Okay, so in this case, the A value, if you look back up at the top, the A value was 0.10 molar. So 0.1 molar to the M and 0.1 molar to the M. Now what's that going to allow us to do? Once again, it's going to allow us to cancel this as well. So all that we're really left with are the values for B. So in this case of these reactions, it's 0.30 molar raised to the N, and the bottom was 0.1 molar raised to the N. So what this tells us is that when you divide 6 by 2, you get 3. So 3 is going to be equal to, and when you divide here, 3 to the N over 0.1 to the N, if you remember your um, the rules for working with exponents whenever you're dividing, you're simply going to be able to write this as 3 dividing zero point 0.3 by zero point 0.1 raised to the n. You can combine it like that. What does that tell us? That tells us that n is equal to 1. So just like we did by inspection, we now know that n is equal to 1. Well, that's important. We have to have that situation occur. Now that we know that n is equal to 1, however, we could do a reaction where b was never held constant. Now that we know its power or its exponent, its order, we could simply fill that in and still solve the problem. You're going to have to do that on one of the problems on your worksheet. So let's go ahead and find A, what m is equal to. This time we used the rate of reaction 3 on top and reaction 2 on bottom. Now remember, now we know that B is 1 raised to the first power. And this is 3, this is 2. And again, we know that B is raised to the first power. So for reactions 3 and 2, the top values 5.4 times 10 to the negative 2 molarities per second. And the value for the rate for reaction 2 is 6.0 times 10 to the negative third molarities per second. Remember, the K's are going to, I'm sorry, that's supposed to be a 2. The K's are going to cancel. They have to be the same. And now we have 0.30, whoops, wrong color. And we know that B is 0.30 raised to the first. This one is 0.10 molar and 0.30 raised to the first. So even if these did not cancel, and they will in this situation, you would be able to calculate the values 0.3 divided by 0.3 or zero point 0.3 divided by maybe 0.2, whatever the situation was, you'd be able to go ahead and calculate that and be able to still solve for m. Now, in this case, it does go ahead and cancel, but I just want you to make sure and realize that this is what you're going to have to do if one of the values, one of the reactants is never held constant. So that's going to cancel. You're going to end up with 9 equal to 3 to the m, which means that m is going to have to be 2. So we now know that m is equal to 2. So we can do it by calculation. All the rest of the answers will be the same. We've already done those. We did that in the previous video, so I'm not going to continue that part here. But I just needed to show you that by doing this mathematically, by doing the calculation like this, we can do more difficult problems and still come up with our rate orders. So the overall rate order for this reaction, since m was equal to 2 and n was equal to 1, simply add those together and we get an overall rate order of 3. So how do we find the rate constant now for this reaction? Well, now we know what the rate order is. We know that rate is equal to K, and both by inspection and mathematically, we determined that it was going to be A squared times B. And to find K now, simply pick any of the experiments and fill in those values for rate, for A, and for B, and you can find K now that we know what our exponents are. Now, I always choose the top reaction. So what I'm going to do is choose this reaction right here. So the initial concentration of A is 0.1, B is 0.1, and it gives us the rate of formation of C, 2.0 times 10 to the negative third. I always use the top one simply because my eyes end up crossing, and I will try, if I try to use one of the other experiments, I'll start mixing up the numbers. So I'm going to use those top values. So we're going to go back here and we're going to fill those in. We have 2.0 times 10 to the negative third molarities per second equal to K. We said both of these values were 0.01 molar squared and 0.10 molar raised to the power of 1. So when we solve for K, I'm going to change, first of all of these molarities to moles per liter, because one of the things they do on the AP test, they will often tell us that all we're going to get a point for is having the correct units for K. They don't even care what the calculation is, so we have to be very careful that we know how to find the units for K. So K is going to be equal to 2.0 times 10 to the negative third moles per liter per second divided by, and I'm run out of room a little bit, but it'll be okay, 0.10 moles per liter squared and 0.10 moles per liter. So I've got all my units here. Now let's think about how those cancel. Now this gets a little confusing, and I'm going to show you a little shortcut for this in a little bit. But notice that we've got moles squared and liters squared here, right here, okay? Those aren't going to be able to cancel because I'm going to cancel this mole and this liter. Those moles per liter are going to cancel, but the moles squared over liters squared is not going to cancel, and neither is the seconds. So when I divide this out, the value that I end up with is 2.0. My units are going to be reciprocal moles per liter. Okay, what do you get when you get reciprocal moles per liter squared? You get liters on top, liters squared on top, moles squared on bottom. Now the way AP writes that is moles to the negative 2 to show that that would be on bottom. And our reciprocal, the one thing that never changes is our reciprocal time. No matter what we do with liters and moles, we're going to end up with reciprocal time still in there in the units somewhere. So those are our units for K in this particular reaction. The next thing it asks us to do is to calculate the initial rate of formation of C in experiment 4. Okay, so what does that mean? Well, let's look back at experiment 4. In experiment 4 over here, notice that we do not have a value for rate. Now, guys, you've got to understand how beautiful this rate law thing is. Because once we know the differentiated rate law, we know what those exponents are, we can take any concentration values for A and B for this particular reaction at this temperature, and without even stepping foot into the lab and wasting any materials or spending any money, we can figure out what the rate of formation of C, how fast this reaction would go. We just need to plug these values in for A and B. So let's do that real quick. We know that the rate law now, we actually know what K is now, so we know it's 2.0 liters squared moles to negative 2 seconds to the negative 1. And we know that we're going to be multiplying that by whatever A is squared times whatever B is in this particular reaction. So going back to this, I've got liters squared moles to negative 2 again, seconds to negative 1, times our concentration of A, which is 0. I've got to switch over my key real quick. There's 0.25 moles per liter squared times 0.15. Now these are all the values that are in reaction 4, remember, moles per liter. When we multiply this out and we start canceling units, we're going to find out that we end up with, because these units are going to, those units are going to cancel. And what we're going to be left with for rate is what you would expect for rate. We're going to get 1.88 times 10 to the negative second moles per liter per second back again, just like the original rate units were. A little bit confusing, and guys, it's going to take some practice to get those units right. But you've got to pay attention to your units. Okay, so let's look at the next one. Okay, the only difference in this one, I'm not going to show you another calculation because I've already shown you one on how to find a rate order by calculation. There's no sense in wasting video time to do that. We would come up with the same exact answer for this that we did before, the fact that the overall order of the reaction is 3 because the pressure of NO has got a rate order of 2 and the pressure of H2 has a rate order of 1. This came up to be, if you remember in the previous video, that rate was K times the pressure of NO squared times the pressure of H2. So 2 plus our understood 1 gives us an overall rate order of 3. So now we can take that equation, we can choose one of the experiments and plug in values for it to find K. So I'm going to start with this again. Rate is K times the pressure of NO squared times the pressure of H2. And plugging in values, I'm going to use the top value from the experiment table again. If you go back and look at the table, you'll see that that top pressure value is 0.020 atmospheres per minute. And that pressure value is 0.150 atmospheres squared for NO and 0.400 atmospheres raised to the first power for H2. So K is going to be 0.020 atmospheres per minute over 0.150 atmospheres squared times 0.400 atmospheres. If you'll notice what cancels, atmospheres cancel. We end up with a numerical value of 2.2. And look what our units end up being. We have atmospheres on bottom squared, so that's atmospheres to the negative 2 since it's on bottom. And we're still going to have our reciprocal minutes always. So there's our value for K. Now let's see what Let's just think about what this rate law does for us if it just gives us general information. And this is something that you might see on an AP test. If a particular reaction has this rate law that we've been dealing with, K equals A squared B, and a reaction is carried out in which A is doubled and B is tripled, what would be the effect on the rate? Well, think about what that would do. If we have this as our rate law, if A is multiplied by 2, it's doubled. What does that do to our rate? Well, since it's raised to a power of 2, that's actually going to be squared. So what we're actually doing is multiplying this by a factor of 4. And if B is tripled, since it's a rate order of 1, we're going to do the same thing to the rate. We're going to triple the rate as well. So overall, what are we doing to the rate? We're increasing it by a factor of 12. So that's how you would report that, or that's the answer choice you would choose. The rate is increased by a factor of 12. Now, I'm going to mention this shortcut on the units. And guys, some of this is not going to make a whole lot of sense, or you're not going to internalize it very well until you practice it. But when we have units for K, it depends on what the overall order of the reaction is. If you'll notice, we have reciprocal time in every situation. We also have liters and moles, generally to the negative something. We always have exponents that are one less than our overall rate order. What does that mean? Look at what happens if it's third order right here. Third order, we have liters squared moles to the negative 2, seconds to the negative 1. That's 2's. It's one less than the fact that it's third order. If it's second order, this is just a shortcut. There's no cosmic meaning to it. It's just a shortcut. If it's second order, we're still going to have liters and reciprocal moles, but one less than second order means those exponents are going to be ones. So liters to the understood first power, moles to the negative 1, and our seconds to the negative 1 never changes. If we have first order, one less than first order is 0. And if anything's raised to a 0 power, whether it's a positive or a negative, it's 1. So both liters and moles drop out because they're raised to 0 powers, and all we're left with is seconds to the negative 1. Finally, 0 order is something that you just have to memorize. Remember, if it's 0 order, it means the concentration of the reactant doesn't matter for the rate. So rate is just equal to K. Well, think about that. If rate is equal to K, then whatever the units for rate are will be the units for K. And the units for rate are virtually always moles per liter per second. Could be moles per liter per minute, but regardless, reciprocal time is always in there. You can also look at the same thing happens with atmospheres. Atmospheres are always reciprocal atmospheres unless we have 0 order, and it's one less than the overall order. So think about this, and this was a question on a multiple choice just a couple of years ago. If we had something like this, rate is equal to K, and we had something really random like A to the second, B to the third, C. Maybe it's something really complex like this. And it asked us to give the units for K in this situation. Well, think about it. The overall order of this reaction is going to be these exponents, understood 1 here, added up. So the overall order of this reaction is a 6. So what does that mean for units? We're still going to have liters. we're still going to have reciprocal moles, and we're still going to have some reciprocal time, always reciprocal time. And if it doesn't give you any other information, always choose seconds. That's by far the most common. And since the liter and mole exponents are always going to be one less than the overall order, those values are going to be fives. Liters to the fifth, moles to the negative fifth, seconds to the negative one. We'd never seen one like that before. Some of the students got it right because they were thinking, outside of the box and realized it was going to be. They'd memorized it that way, one less than the overall order, and that's what their units for K were going to be. So keep that in mind.